All right, so I'm going to show you how to write some functions, a simple function in Matlab. Then after, I'll teach you how to also write a Matlab function for a differential equation, and then how you can run it as well with several plots. So let's just say we want to solve a simple parabolic problem. Basically, that means we want to solve a problem of the nature, let's say y is equal to some ax squared plus bx plus c. So let's just say this is a problem that we want to solve. Y is equal to ax squared plus c. Of course, we know that the parameters here are a, b, and c. So, and of course, another thing we need is an interval space of x. So we need x, right? So let's just say we want to plot for a given, for giving some x as well as some parameters, we want to plot y. So in such a case, of course, you can decide to just write this on your command line. And by that, I mean, you come here and then you write some x. X is equal to, let me say, minus 10, interval 1, interval 0.1 to 10, right? I create a vector, and then I can initiate some coefficients. My a, I say if my a is 1, my B is maybe 0. Let me say my B is plus 1. And then my C is, let's say, minus 6. Okay. So basically, here I'm trying to plot an equation of y is equal to x squared plus x minus 6. Okay. So in that sense, once we have this, of course, the next thing is that we want to write for our y. So y is some a times an x squared. And then, okay, because x is a vector, so I vectorize it with a point, with a pointer, x squared. Then I have some b also, b times x, and then plus a c. Okay, and then now I can plot my x against my y. I use some options here. So I do red, I star, a dash dash, and then I close it. I can do also line width. So you can do a line width, then line width, let's say line width 2, and then you enter your plots, and then you can see the plot function, right? This is the plot function. Of course, what you can do with a plot is that you can add, let's say, some other things about the plot function. You can add a title, you can add a legend, you can add many other options that you can add to your plots. So let me go back quickly and then show you what this plot function is. Okay, so let me put this somewhere inside there so that you can see what happens. Let me clear off everything from my screen. Okay, good. So now we see this here means plot x against y, and then this parenthesis means that this quotation means everything here means plots color red, use some stars and as pointers, and then a dash dash, make the width of the line 2, right? So of course we can change this. We can do another plot, and maybe now we do plot xy just for us to see blue, and then a diamond, and then a dash, and then enter. Okay, just for you to see now, you see that the plot's description changes. Of course, as I said, you can do an X label and you can put a label on the X axis. So for X, I say this is our X, right? We can do for Y label as well. And then for Y label, let me just write Y. And then I can give a title. A title here means a plot of X against Y also there. So you can see these are some very basic things that we can do. But of course, the question really, what we want to do next is what happens if I want to use the same y that I've given here, y is equal to ax squared plus bx plus c, and now I want to change the parameters of a, b, c. Do I have to go back again and type all these things again? Yes. And that is why we have something we call functions. So functions helps us to kind of make nicer definitions and write nicer codes that we can use, we can call whenever we want. So here, let's just say we want to write this same thing now in a function, right? So let me call this for function, let me call it a function. Then usually for a function, you need an output argument, right? An output argument as it returns something. And then let's call this parabola pow, right? Pow parabola. And then let's put the parameters A, B, C in there, okay? So here we have a function. The name of the function is parabola pow. And then if we put this, if you call parabola pow, it will expect some input argument. It will expect A, B, C from the person. So here already what we can do here is first that we can start with our X exactly as we have here. Let me just copy and paste. So we can have our X, right? And then we can have our Y equation as well. So we can have a Y equation, and then we can have a plot, right? So we can have a plot, or we can have a plot, a label, and so on, okay? And an end, right? So now if you save, it saves the function name is what is saved here as you can see here, parabola pow. So if you save it, let me do some just for easy understanding. So now this is the function we have. So in this case, then, in fact, in this case, since we are not expecting any output, we don't put any output here. So in this case, what you do is if you write here parabola, right, parabola pow, and then you put in some values, let's say 1, 0, minus 9, for instance, and it plots, then you will see the plot. So then we will see the plot, right? So this is the plot for this function. For a function y, so this function that we've plotted here now looks like y is equal to x squared minus 9, right? This is what it means. This is A, B, and C. So whenever you write A, B, C, parabola pow, and you put something in there, 3 parameters, it gives you a plot for that, right? So this is what a function does in that sense. So very, very easy. If it is too much, what we can do, we can go back to the function. We can decide that, okay, maybe we should just plot, just do a plot, right? Nothing fancy, right? So in that case, if we come here again and we do parabola power, parabola power, and now we do 1, 0, minus 4. We can see the plot again. We see now nothing fancy, just a straight line. simple plots, right? So that is what we mean by functions. But it's not the only function that you can do. There are other functions as well that you can do. So for instance, if we come here, we can do the Lorentz function, right? And now this is an ODE. So the Lorentz function basically is a function that consists of, let me call it the x, right? The t for equation 1 to be minus sigma x plus sigma y. Then there's dy dt, which is equal to rho x minus y minus xz. Then there is a z dt, which is equal to minus beta z plus xy. So this is the Lorentz equation, right? So to implement the Lorentz equation, now we write a function for this system here, this dynamical system. So we call it function. Now we expect an output because in the end, we expect these values, right? So we have x prime is equal to power Lorentz, t, which is the input. Got this here, we have t here, we have the time, and then we have some x, y, z, and then we also have some sigma, some beta, and rho. These are the things that we have so far we need in this differential equation. So what we do is that we create x, when now we have our x is now going to be an x1, x2, and x3, right? Which corresponds to x, y, and z, right? So let me call it x prime, which corresponds to x, y, x, y, and z. So wherever we see x, we put x1. And wherever we see y, we put y1, x2. And wherever we see z, we put x3, right? So basically, this equation here, we can rewrite it in terms of x1. Here is also x1. Now this guy becomes x2. This is also x2. And now this is x1. This is x2. And here now we have x1, x3. Here we have x3, we have here x3, and then here we have x1, x2. So we can rewrite this whole equation in terms of x1, x2, and x3, where we have said that x is now consisting of some x1, x2, x3. Okay, so in that sense, we can rewrite. Of course, we can fix the parameters, all the parameters. So these are the main parameters that are involved in this state: sigma, beta, and rho. Right, sigma, beta, and rho. These are the main parameters that are involved in this kind of work. Okay, so in that sense, we can rewrite this whole differential equation in the Matlab sense. So we have x prime is equal to power tx, where now we have sigma, which is a parameter here. Sigma is 10. We have rho. We have also given rho a value of 28. We have beta. We have given 8/3. And now the equation itself, this equation here, how do we put it in MATLAB here? So we write x prime, and then as I told you in MATLAB, we write a vector, or we write a matrix where we separate them by semicolons, right? The element in the matrix, the rows are separated by semicolon. So here the same. Now you see that first row corresponds to equation 1. This equation 1 that we have from our differential equation. So the first row is equation 1. The first row here is, let me call it L1. This one is L2. This one is L3, right? So equation 1 is minus sigma times x1 plus sigma times x2. So you can see it directly as equation 1. Or you can write, and then the second row is row x1 minus x2 minus x1 times x3, which is exactly what we have done here. And then we have beta minus beta times x3 plus x1 times x2 as row 3. Then now we put the brackets to cover, right? We put them in a bracket. So we separate each of the equations by a semicolon and make them a row. So if you have 10 or whatever, any number of states, you can write all of them in the same manner, just that you also have to make sure you have some x1, x2, and so on up to some xn. The number of equations and variables that you have. Okay, so we write it as that. Then now, if we want to call such a function, so let me clean the screen so far. So if you want to call such a function, now what we do is we go to the command. Once we finish writing our function here, which is the power Lorentz tx x prime is as the output argument, and then we declare our parameters sigma, rho, beta, and our system of equations here. Every line of every equation will take one row. Then after that, what we actually need to do now is then to run this function. How do you run this function? So for every differential equation, you need, for every differential equation, you will need initial condition, right? You need initial conditions. So here, the initial condition, I call it init. So this is really the initial condition that we need. Bear in mind, for 3 equations, for our system of equations, we will also need a corresponding initial conditions for each of the variables, right? Each of the states. So for instance, here we have x here. This one corresponds to x1 of 0. This will be x2 of 0. And this one will be x3 of 0, right? That is, we need that. And then we also need a time span. How long is your simulation going to be? So usually we have here your time, and then here you have your x axis as well. So we say, okay, we want to start from 0 up to 20. Now, to solve the ODE, what you need is an ODE solver. So in Matlab, there's ODE 45. ODE 45 corresponds to a Ranjikuta solver, a Ranjikuta 45 solver. So of course, there's ODE 23 as well, also a Ranjikuta solver. And there are some other solvers there as well. So here we call this solver ODE 45. And now you see we have at power Lorentz. The power Lorentz here is the function, right? Is the function that we wrote here. And then now it takes the time span and then the initial condition, right? So that is what that is all that is needed. Then now when you run, so we run it. If we run it, then of course I do not output the T and the Z, but they are there. So we run it, and then you see everything is working fine. What we can do even is we can do some. Okay, then now we can plot. For instance, x1, and then we can plot x3, right? x1 against x3. And now we see the picture here. Well, of course, maybe I already plotted it for you, but I can modify, and then I make a coloring, a bit so you can see it clearly. So you can see it clearly. So this is x1 against x3. Of course, here you can see already that here I am the x here. I'm writing x1 to be x1, and then I'm writing x3 to be this, right? So basically means that we have the x. If I show the x, you see that it is a there's an n by 3 matrix, right? So because what we do is we take the initial condition, we take the initial condition. So we take the initial conditions that we started with. So we said that init was equal to -8 was 8 and 27. So those are the initial conditions. That's where the simulation starts from. So here you can see it starts from -8, it takes 8, and then it takes 27. And now we give a time span. We give a time span from 0 to 20. So we do ODE 45 and solve each of these intervals from 0 to 20, and then we plot. So this is what we get. So this is for x1, this is for x2, this is for x3, right? And then to call them, because you want to call the first column of x, we write x, all the rows, and column 1. If you want to call column 2, it's x, all the rows, and 2, column 2. If you want to call column 3, all the rows, and 3. So this is how we call them, right? Okay. So now what we actually do is that we we can plot several other things. We can plot several other stuff from this. So we can do subplots. So subplot means you can do a lot of plots within one plot, so one figure. So if we do, for instance, we can do subplot 311. So subplot 311 means that 311 means you should create a 3 by 1, right? You should create a 3 by 1 plot. So here it says create a 3 by 1. So it means you are going to create a figure, right? 3 by 1 means 1, 2, 3. Of course, if I did 1 by 3, if I did subplot 1, 3, then it is going to be 1, 2, 3. So this is the number of rows, the number of columns, and then this number here is the numbering of the figures, right? So if you do 3 by 1, then this is 1, this is 2, this is 3. So if I put here the number, let me put n here, then that is where the plot goes to, right? So the same thing also for here, for this one is the same case. So let's do an example so we see how the subplot works. So for instance here, subplot 311, I can say plots, right? Let's say plot t against x1, right? T against x1. Okay. So if we go to subplots, you see 311 t against x1. And then let's go there again. Let's do subplot 312, right? Let's do subplot 312, 312. Now let's plot t against x2, right? Subplot 312, let's plot t against 312, 3 against t against 2, right? Now let's do this as red. Okay, and now let's go and see the figure. Now you can see this is 1, this is 2, and now it's 312. So the third one will come down, and then now we can do t against x3, right? T against x3. T against X3. This is good. Right, so if I go here, then we see, so you can see the subplots, how to use subplots, right? Of course, if I had done 1 by 3, then it would have been 1 row, 3 columns. But this is 3 by 1, so it's 3 rows, 1 column, right? Of course, we can do 2 by 2, just 2 rows, 2 columns, based on what we want to show. Right, so we can do the same thing again. Let's do the same thing again. And now let's do two. Let's say this is a 2 by 2, right? A 2 by 2. Then let's plot that. Then let's do this. It's a 2 by 2. So let's do this. So now this is a 2. This is a 2. Let's do that. And now the green one is a 2 by 2. So let's do that. It's a 2 by 2 plot. Right? So now what do we put in the fourth plot? Now we have this one. We can now put, it's a 2 by 2, so we can put number 4. And now let's plot X1 against X3. Let's call it magenta. So you see, this is how you plot. You can do several plots on the same, on one figure, right? On one figure. This is how we do several plots on one figure. So good. So of course, we saw, so for instance, in our power Lorentz function that we wrote here, in this function that we wrote here, we saw already that we wrote power Lorentz, the time, and then the x, and then now we have x1, x2, x3 that we wrote now. And then we have these parameters, sigma, rho, and beta. So in essence, it means that whenever we want to run new parameters, we need to go back to power Lorentz and change the values for these parameters. And whenever we want to change all the parameters, means we have to go back again and change and change. So another way we can do it is actually to write the whole function and now introduce the parameters there. And that brings us to this new one, So where now we write the whole function with the parameters, right? So let's go there and we see. So now in this new function, you see that, right? The function is x prime is equal to power Lorentz 1, the time x and p. So p here corresponds to the parameters, right? And then this p, I say that sigma is equal to P1, beta is equal to P2, and rho is equal to P3. So the similar thing as we did, we wrote x, right? X1 was equal to x. We wrote x2 was equal to y, and then we wrote x3 was equal to z. So similarly, we have P1 is equal to sigma, and then we have P2 is equal to beta, and then we have P3 is equal to rho. Okay, so now we can rewrite equations now with this ideology that P1 is sigma, P2 is beta, P3 is rho. And then when we do that, then we are able to now call our function with the parameter. Okay, so in that case here, so now, so we have the parameters as P, let me write it here. So where P is the parameters for our model. So now, how do we run this model again? Of course, to run an ODE, you need initial conditions. So again, -8, 827, we take that as our initial condition. Then we need the time, the span. So again, we take 0 and 20. Again, for time span, and now we take the parameters P. So in Paul Lorentz, the parameters were 10, 28, 8/3. But we should know that in this particular case, P1 corresponds to sigma, P2 is beta, and P3 is rho, right? So it means that if we do sigma is 10, rho is 28, and then beta is 8/3, we need to arrange it similarly for how the p's are arranged. So sigma is 10, and then beta comes next, so beta is 8/3, and then rho comes next, which is 28. These are the parameters. Then we can run again our model, which is ODE 45. Now we have Paul Lorentz 1, right? So Paul Lorentz 1, what does it need? Paul Lorentz 1, we need a T-span, right? We need the inits, the initial values. Then we put this here, I will explain, and then we put our P here, right? So this bracket we put here, which is an open bracket, is purposely because of how Matlab the command for ODE45 is written. So it expects after initial condition some set values. So these set values, you understand them when we start doing the theory. So you understand the tolerance, right? The relative tolerance for which convergence should occur, or the absolute tolerance for which convergence should occur, right? So Matlab as a default, I think is 10 to the power minus 3, 10 to the power minus 6. These are some values that you can use there. So here we just say use the default tolerance. Okay, so in that sense, we finish running, and then now we can plot again. We can do similar plots as we did, right? We can do similar plot as we did. So we can do again subplots, right? You can do a subplot 2 by 2 by 1, and then we can do plot t against x1. Red. Okay, then subplots by 2, and then now by 2, and now let's say blue. And then subplots again, the third one by 3, let's say magenta. And now a fourth one by 4, then let's do x1 against x3, and now let's do green. Let's do sun. Okay, so we see how the plots look like if we plot time against x, time against y, time against z, and then x against z. So this is how we do these simulations.